All right, welcome to section 1.5, solving quadratic equations with me, Mr. Hain. All right, so what are quadratic equations? Quadratic equations can be written in this form. So some number A, B, or C, these are just real numbers. So they could be net fractions or decimals or integers. So any number times an x squared plus or minus any number times a x and plus or minus a c, and we typically have them equal 0, and you'll see me reinforce this topic as we go through. Again, in green you see a, b, and c are just real numbers, fractions, integers, or decimals, and the key is that there's an x squared, that's to the second power, somewhere in that equation. So here's some examples. It looks like there is not a c here, but the c is actually 4, and we can move that over. 2x squared equals 250 is definitely a quadratic equation. Don't feel weird that there's not an x, it's just the coefficient for b, or what b is equal to, is just 0. The key again is that we have an x squared term. This is also a quadratic equation. I know you don't see an x squared term in it, but what you do see is that you have two binomial terms multiplied by each other. Now, if I were to multiply 2x times x, I would again have 2x squared, so that is a quadratic equation. Another example here, you see that I have a binomial term, but it is squared. This is also a quadratic equation because I know that if I have 2x times 2x, it would be 4x squared, and so that is another example. Here we have a very traditional example that looks almost exactly like what I have in blue, and we're going to launch directly into solving by factoring and the zero product rule. Now, the book and the text does call it the zero product principle. They are one and the same thing. In example 1, you see that I have 3x squared minus 9x is equal to 0. So here, a is equal to 3, b is equal to 9, and c is equal to 0. Not the equal 0, but there is nothing here. It's not plus or minus something before the equal 0, so the constant is 0. I guess you could make an argument that they're both the same thing, but I just want to highlight that fact. So what we're looking at here for factoring is I want to see if there is a term, what factors do 3x squared and 9x have in common? And that factor is 3x. If I do 3x times x, I have 3x squared, which is in the original term here. And if I have 3x times 3, I'll end up with 9x, which is the second term of my original equation. Now, doing this is very powerful because we see, we know the zero product rule. Basically, all the zero product rule or zero product principle says is if a product is equal to 0, which is what we have here, 3x is a factor and x minus 3 is a factor. When you multiply them, they equal 0. So if a product is equal to 0, then one or both of its factors are also equal to 0. So that's what this is saying, either a equals 0 or b equals 0 for this to be true. So I can take the first term here, 3x, and I can set it equal to 0. And I can take the second term, x minus 3, and also set it equal to 0. This will allow me to solve for any value that x could possibly be. And then you see here in purple and black, I've gone ahead and solved it. Here I just divide each side by 3, x is equal to 0. Here I add 3 to each side, so I have x is equal to 3. So I have two solutions, x is equal to 0 or to 3, and both of those make the original quadratic equation true. That's example 1a. We're going to keep on going. Example 1b, it does look a little bit similar. It doesn't equal 0, so I'm going to move the 1 by using the inverse or opposite operation. So here I've subtracted the 1 from each side, and I have 2x squared plus x minus 1 is equal to 0. Now I'm going to do another video probably this weekend or on Monday if I can have time, so I can further explain the Xbox method, which should be a review. There are many different ways that you can factor three-term quadratic formulas. This is just one way of doing them that is commonly used in all the school districts in California, so this is the one that I'm reinforcing. So here you see that the top number, a times c, is just 2 times negative 1. I put the whole term here, negative 2x squared. And the bottom is a plus b. So it's just, I'm sorry, it's not a plus b, it's just b. So here it would just be 1x. So in other words, I'm looking for the two terms, the two numbers that would fit in this box that would multiply to negative 2x squared, but add up to 1x, which is again right here, it is just a b. And that's 2 and negative 1. Now the original terms here on the diagonal come from the original equation. So 2x squared you see comes here to 2x squared. And the negative 1 you see comes down to negative 1. All I'm doing now is seeing what I can factor out of each row and column. So in the first row here I have 2x squared and 2x. I can factor a 2x out of them. And in the bottom row, the only thing I have in common is the negative sign, so I factor out the negative. So 2x minus 1 becomes my first binomial term. And on this column, 2x squared and negative x, the only thing they share is an x, so I factor out the x. And here, these have nothing in common at all, so I factor out a positive 1. And so this x plus 1, or an x and a positive 1, becomes my second term here, and I set that equal to 0. That allows me to use the zero product rule, or the zero product principle, and solve for x. So here you just see me doing inverse operations, and I have x is equal to negative, or positive 1/2. And here I have inverse operations again, and x is equal to negative 1. All right, so x is equal to negative 1 and 1/2. So now we're going to move on to solving by using the square root property. And we use this specifically when we have a formula that does not have a b, no b, and what I would term as no c. So some number times a variable raised to the second power equaling an n, or another number. And this is a perfect example. The a here is 3, and the n here is 21. You see I have an x squared. So again, it reinforces that I only use the square root property when I have something like this. A number times a quantity squared equals another number. So I'm going to isolate the x squared term by dividing by 3 on each side. So now I just have x squared is equal to 7. And I square root both of the sides now because the square root undoes the square. So I square root each side, and I have x is equal to positive or negative, or plus or minus the square root of 7. Now, this is two separate solutions. I really don't mind if you write it like I have here in green, but I want to reinforce now in this specific video that they are two separate answers. And that, again, is due to the square root property. You always add the plus or minus when taking the square root or any even indexed root, because you can see if I just do the example of square root of 16, 4 times 4 is definitely 16, so that's an answer. But negative 4 times negative 4 is also 16. So that's why I have plus or minus the square root of 7. And that's example 2a. All right, so another example using the square root property, and again, we just have, it needs to be some number and an x squared equals another number. And here, I need to move to isolate my squared term. So I subtract 45 from each side, and then I divide each side by 5. This leaves me with just the squared term x squared equals negative 9. Now, this is very different than the last one, but again, it is the same because I have a number, or in this case, I've isolated the x squared term. So it's just a 1 in front of the x squared, equaling a number, which in this case is negative 9. So I can take the square root of both sides, but see, the negative root results in an imaginary number, or I. So whenever I see a negative underneath a square root, I'm always going to, and I say this all the time, pop my I out. So whenever I have a negative number inside a square root, I pops out as the answer. And again, we know what the square root of 9 is. 3 times 3 is 9. And so I have, again, plus or minus 3i, because the square root property, again, same example as before. So I have two answers here. One of them is positive 3i, and the other one is negative 3i. Excellent. So that's how you deal with a negative in a square root. That's just reinforcing the square root property. Again, it's plus or minus. We have a third example. Now this one looks very, very interesting. And a lot of students get confused about this because they think that they have to FOIL what is inside the binomial term, which is x plus 5. And I get some awkward answers here. But really, when you think about it, this squared term is literally just x squared. In this case, x is just x plus 5. And it equals a number. So this is absolutely solvable by the square root property. In fact, I love seeing problems that look like this. So let's square root that x plus 5. And a lot of people get really creative when they see this part here, but don't be. When you use the square root, it again undoes the square, so all that I'm left with is the x plus 5. What I do to one side, I have to do to the other. And so x plus 5 is equal to plus or minus the square root of 11. And again, the square root property, it's always because I have to add the plus or minus, so I'm taking the square root of a number. And I just isolate the x. So now I just want to find out what x alone is equal to. And again, you see here, I didn't say 11 minus 5 was the square root of 6, because this is a root. This is an actual number. You can put it in your calculator. It's probably 3.4 something or 3.5 something. I'm just guessing off the top of my head. But it is a number. So I have to represent that with the square root of 11. So this minus 5, it's a lot easier than a lot of students think. You're just saying negative 5 plus or minus the square root of 11. And that's your answer. That's it. And that's two answers, because I have negative 5 minus the square root of 11 and negative 5 plus the square root of 11. So again, I have two answers here. But it was very simple. I didn't use a quadratic formula or FOIL at all. So I'm excited when I see problems that look like checkpoint 2C. So reaching back into high school math for some, or into many years ago math for others, we have completing the square. And this is extremely powerful, but this is just examples of the method that we use to complete the square. So I have three different examples here. Now, full disclosure, the one I really like is A. I'm really only going to ever ask you guys to do quizzes and complete the square with things that look like example A. Where in this case the coefficient of the x squared term is 1 and the b term is even. But because the homework has other examples that ask you to complete the square, or because you can just complete the square when you see problems that look like this, I'm going to show you how we can complete the square with A, B, and C for this example. Alright, so both of them, all three of these start by dividing b by 2. So 6 divided by 2 is 3. Negative 5 divided by 2 is just a fraction, negative 5 divided by 2. And 2/3 divided by 2, all I really need to do is multiply the denominator by 2, which gives me 2/6, or yes, I know, 1/3, if you've already reduced that fraction. In each of these cases, I square the quotient, in this case 3. 3 times 3 is 9. To get, all I'm doing is adding this, the square of half of the b term to the end of the expression. So I have x squared plus 6x plus 9. I square this, so 5 times 5 is 25. A negative and a negative, when I multiply, make a positive. So 2 times 2 is 4, so I have that here. And again, I've just added that to the end of this expression. And again, here I've also squared the quotient. 4 over 36. If you already reduced your fraction, it would also just be 1/9, and I just put that here as well at the end of my expression. The reason that we complete the square is because each of these quadratic expressions that we've now created by completing the square is a perfect square binomial. I can just factor it like that. So you see this 3 is how I got the plus 3. It's positive, so it's plus 3. X is because X is my variable. If I square this, if you want to take time and pause the video, pause it and FOIL that out, you will absolutely get what's in the red box here. Same thing goes for example B. The original quotient is negative 5 divided by 2, and if I drop that down, you see it's negative, so I have a minus 5 over 2, and x because x was my variable for example B. And here again, you see 2/6. If you put 1/3, it's okay. Same exact fraction, and I just have here x plus 2/6 squared. And again, all of these are really cool because if you think about it, they look kind of like example 2C. All right. So here's why we complete the square. It's a powerful, powerful tool. And we can use this method again when a is equal to 1 and b is an even number. So in checkpoint 4, a, the coefficient of x squared, is definitely 1, and b is an even number. So see that here, and b is definitely even. And I want to move c, and I'm going to leave some space because completing the square, you remember, we actually created a number that went here. So if you recall from before, I'm going to divide 4, or b, by 2. That gives me 2, and 2 times 2 is 4. That's a positive. It's always going to be adding when we add it. And when I add the 4 to another side, what I do to one side, I must do to the other. And so I add 4 to the other side, because that's 4 divided by 2, which is 2 squared. Again, 4 and 4. This gives me x plus 2 squared. So here I have exactly what I need. All right. So I have x plus 2 squared is equal to 5. And this looks exactly like checkpoint 2C. It's the square root property. So I'm going to square root both sides, move the 2, solve for x, negative 2 plus or minus the square root of 5. And that was much easier than using, in my mind at least, it was much easier than using the quadratic formula. So we're going to complete the square. Again, this is going to be some challenge and extension. So if you want to skip ahead past this example, there are homework questions that look like this. Again, I'm not going to count off if you didn't do those questions. At least show me that you tried to do those questions, and I'll be fine with that for your homework. I see here that when I complete the square, a has to equal 1, so I'm going to divide everything by 2. So if I divide everything by 2, I'm going to end up with a fraction. So a is definitely 1, and I have a fraction, 3 over 2. When I divide by 2, I multiply the denominator by 2, which is how I got 3/4. I add this to both sides. For some reason, the 9/16 didn't appear here. But it's not a problem because I know that this whole term, the whole quadratic, factors to just x plus 3/4 squared. And 2 wholes, if 16 is my denominator, would be 31, or 32. So 32 plus 9 is equal to 41 over 16. And yes, it's a fraction, and I am going quickly because this is challenge and extension. But you see here, I can just square root both sides. That just drops this out of the square root. And when I move the positive 3/4 to the other side, I have negative 3/4 plus or minus the square root of 41 over, okay, and then you see a 4 here because 16, the square root of 16 is 4. And there you go. All right, which brings us to what I like to call the hammer of Thor, or Molinar. Yes, I am a geek. All right, I love it. Embrace it. I have the quadratic formula, which is a lot of how many of us just learn how to do this in school. Again, I'm going to reinforce this is how we have to set up our quadratic equations. If it's not equal to 0 and it does not have any, and it looks like a number times x squared plus or minus a number times x, plus or minus a number is equal to 0, then you cannot use a quadratic formula. Make sure that it looks like this. And again, we have our good friend, the quadratic formula. On any quiz or test, I'm not going to hold you to memorize this quadratic formula. I'm going to write it right down for you. All right. So here's the example. I have 2x squared plus 2x minus 1 equals 0. And yes, again, that is indeed in this format that I see in blue. A is 2, B is also a positive 2, and C is the negative 1. I'm just going to substitute all those parts into the quadratic formula. You do see this is the opposite of B, or negative B. So since my B here is a positive 2, this will turn into a negative 2. And plus or minus the square root of b again, which is 2 squared minus 4. The 4 comes from the quadratic equation. 2 is a, and negative 1 is c. And I have 2 times 2, again, because a is 2. So working to simplify, this second part just becomes a positive 8. Negative 4 times negative 1 is positive. Positive 4 times 2 is 8. And I have negative 2 plus or minus, and 2 times 2 in the denominator is 4. And 4 plus 8 is 12. Now, many people will see that the square root of 12 is actually the square root of 4 times the square root of 3. That's 4 times 3 is 12. And we know what the square root of 4 is. It's 2. So that's awesome. I can, now that I have that 2 and I've simplified this radical to 2 times the square root of 3, I can cancel, because I can factor a 2 out of the bottom, and it cancels the 2 here and the 2 here, leaving me with negative 1 plus or minus the square root of 3 over 2. Excellent. So this is just simplifying a radical expression. Again, we have another example. Now I could complete the square because a is equal to 1 and b is even, but I'm going to solve using the quadratic formula. You get the same answer. A in this case is 1, b is negative 2, and c is a positive 2. So again, because the equation says negative b, since my b here is already a negative number, when I plug it into the equation, it is positive 2. And then you see I plugged in all the rest of the values here. And I simplify a little bit, and you see I have a negative in my square root. So recall from earlier in this video that when you have a negative under a square root symbol, an I pops out. So here we go. I have 2 plus or minus 2i, because the square root of 4 is 2 over 2. And I can cancel those 2's. Now I have to cancel both of them, and I get 1 plus or minus i. Same answer that I would get if I completed the square. That brings us to the end of today's video for section 1.5. In review, make sure that you have gone back over the video if need be. I know I'm flying through in reverse. I'll probably do this every single time. And review each of the principles that we have, but that is what I have for section 1.5 quadratic equations. And if you complete the homework on the syllabus, all of them flow from the examples that I have. Please do not do number 109 if it is still listed as homework for section 1.5. As it was not covered in the video, I will not be asking a quiz or test question about something like that. Excellent. I will see you guys next time.